What is a buffer? You're not allowed to answer. Because I have a feeling you're going to tell me exactly what I want to hear, and I want to get other people's answers first. What is a buffer? Okay. That's what a buffer does, yes. A buffer resists changes in pH. What else can you tell me about buffers? Nobody? Bueller. Bueller. Oh my gosh. It's not a Christmas reference. Your homework assignment over winter break is to watch Ferris Bueller's Day Off. It's a classic. It doesn't matter. That is your homework assignment. All right. So a buffer, it one of the properties of a buffer, which was correctly identified, is that it will resist changes in pH. It keeps the pH constant, roughly. Would you like to add anything? What? Oh, cells. I heard sols. 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 Yes, cells in our body have buffers in them to prevent the pH from changing. Yes, that's an application of a buffer. But what is a buffer? But that's what a buffer does. How can you describe to me what's in a buffer? Kind of. You're getting. You're like 70% correct. Okay, 50% correct. A buffer does contain a weak acid or a weak base, but it has to have one other key component. What? It's salt, so or it's starts with a C. It's conjugate. So you have to have a weak acid and its conjugate base, or a weak base and its conjugate acid. You have to have both of those in solution for them to be considered a buffer. And we'll talk today how they resist changes in pH. Okay? So, to calculate the pH of a buffer solution, you can do a rice table, or you can use a formula that looks like this. Does anyone know what this formula is called? The Henderson-Hasselbalch equation. Okay, that formula is on your formula sheet, so no need to memorize it. What you need to know, though, is how to use it. Okay, so what do you think HA represents? A weak acid. So HA is the weak acid. If HA is the weak acid, what does that make A minus? The conjugate base. Yes, it could be the weak base on the top and conjugate acid on the bottom, yes. But it's the acid and the base, and it has to be a conjugate acid-base pair. It can't be just like any weak acid and a conjugate base. They have to be the conjugate base of the weak acid. They have to have that common ion, all right, in order for a buffer system to work. How do you find pKa? No. That you found pKa of your previous lab by doing the average pH, but negative log of Ka is how you find pKa. So you have to know the Ka of the weak acid, and if you do negative log of that, you can get the pKa. All right. So let's look at this problem. We have a buffer system, a solution that's 0.53 molar HC6H4NO2 and 0.50 molar NaC6H4NO2. Let's identify what our two substances are. HC6H4NO2, what do you think that is acting as? That's my weak acid. And therefore my conjugate base is what? Is what? No. What's the conjugate base? C6H4NO2 is not correct because you have to have a charge. Negative. So we get rid of the Na. Remember when we were talking about salt hydrolysis last time? Whenever you have an alkali metal, a halogen, or nitrate, those are going to be our three common ions that are going to be in salts. You can actually just get rid of them for multiple reasons. If you're thinking in terms of this acid-base stuff, those substances are products of strong acids or strong bases, therefore they don't react with water, and we can ignore them. If you think about it in terms of net ionic equations, those ions are spectator ions, so they aren't involved in the reaction, so they aren't involved in this buffer system. They're still there, they just don't do anything. Okay? All right, so all we care about is the C6H4NO2 minus. Okay. So now we can plug this into our equation, but before we do that, we need to calculate the pKa. So I need to look up in a reference table, or maybe the problem, hopefully the problem would give it to us, the Ka of this. And I'm just going to give it to you guys. This one's actually not in our textbook. The homework problems are, though. Okay? So if the Ka is 1.7 times 10 to the negative 5, what is the pKa? Negative log of that. So we would start off the problem. pH equals negative log of 1.7 times 10 to the negative 5. What? Plus log of what value is going to go on the top? 0.50. And what value is going to go on the bottom? 0.53. Because this 0.50 is the concentration of our conjugate base. 0.53 is the concentration of our weak acid. Okay? So go ahead and do that calculation, please. And what do we get as the pH? 4.74? So that's how you use the Henderson-Hasselbalch equation. Cool? Are we ready to do the next problem? Just about? All right. So this one, we're going to be calculating the pH of a solution that is 0.245 molar NH3 and 0.245 molar NH4Cl. So what substances do I have in my buffer? NH3, which is what? Yep, that's my weak base. And, oh, I said NH4Cl. I meant NH4NO3. Sorry. I was trying to remember the problem. Yep, NH4 plus is the part we care about. That's the conjugate acid. Remember, NO3 is going to be a spectator. You can just cross it off. You can ignore it. It has to be there. Like, I can't go into the back stock room and find a bottle of NH4 plus. It doesn't exist. It always has to be paired with an anion. However, I can go back there and find a bottle of NH4NO3. Okay? So if I used it, the NO3 would be a spectator. It wouldn't be involved in the reaction, but it has to be there. You have to have something to balance out that charge. Okay? So notice that this one, like if this were a problem, you would also be given Kb of NH3. But wait, we need Ka to find pKa, right? In this equation, the Henderson-Hasselbalch, we need Ka. I gave you Kb. What is the relationship between Ka and Kb? Good. I'm going to insert a page to write some stuff down before. So we know that Ka times Kb equals Kw, right? What else does Kw equal? Yeah, it's 1.0 times 10 to the negative 14. That's on your formula sheet. Is there another formula that we have that involves Kw? Yes.
Why would she ask
The answer to that is yes. What is the formula? H plus times OH minus also equals KW. Now, is there a relationship between pH and POH?
Yes.
Yeah, what is it?
pH plus pOH equals 14.
All right, so can we derive the relationship between pKa and pKb from the given formulas? If H plus times OH minus equals KW, and Ka times Kb equals KW, and pH plus pOH equals 14, therefore pKa plus pKb equals 14. Now, Ka times OH minus will not necessarily equal KW. Okay? But these are all relationships that exist. So, in finding your pKa of the problem that we're doing, of this problem, you could find pKb first and then subtract that from 14 instead of using KW. You could use either one. Okay? So, what would be my pKb? Yes, that's how you find it, but what would it be? Calculate it. .74, and then we subtract that from 14 to get my pKa. So what's my pKa? 9.26? So now I'm ready to actually do the problem, right? So let's write out the Henderson-Hassbach equation. pH equals pKa plus log of what substance is going on the top here? NH3. It's always the base over the acid. So B over A. Ba. Okay, always the base over the acid. Always. Always. Okay. So pH equals 9.26 plus log of, what's the top number? 0.245 over 0.245. What do you notice about that? The concentrations are equal, so anything divided by itself is 1, and log of 1 is 0. So therefore, my pH equals 9.26. So when the concentrations of both of your components of your buffer are equal, pH equals pKa. Where else have you recently come across pH equaling pKa? In the lab that you just did, not just the post lab, the entire lab, you had pH equaling pKa. That's because in the lab you just did, you measured out your acid, like the solid acid, you dissolved it in water, and then you took exactly half of it and neutralized it with sodium hydroxide. And you converted that weak acid into its conjugate base. And then, even after we fixed the mistake, we mixed it back with the other half of the acid that we had. And so you had equal concentrations, and then that's why you were able to just measure the pH, and you're like, oh, pH equals pKa. Okay. Now, you probably did not get exactly the same concentrations of both because you're high school chemistry students. You know, you're still learning how to have proper lab technique, but that's, you know, a skill that we're developing, right? So that's why your pHs might not have been exactly the same for all three trials, and that's also why your pHs might not have been exactly the same as the pKa in that chart. But it should have been close, Should have been pretty close. If you got it right on, that's great. Okay? Cool? But that was your lab. So if in the heat of the moment, if this were a test question and you forget that anything divided by itself is 1, or you forget that log of 1 is 0, if you do this calculation, you'll still get 9.26. Okay? All right. Let's look at this one. All right. Let's identify our substances in our buffer. What's our acid in this buffer? Acetic acid, which is a weak acid. So there's my acid. And what is my conjugate base? The acetate ion. So what can we cross off? Na. And there's my conjugate base. Now, what do you notice that's different about this problem? Yeah, we're told the exact volumes that we're adding. So, whenever you are changing, when you're mixing two solutions together, what happens to the concentrations of them? They get diluted. Our acid and base is going to be diluted here. But are they going to be diluted by the same ratio? But look at the volumes. We're starting off with 20 milliliters of each, and we're ending at what total volume? 40. So both of these molarities are going to be divided by 2. So is the ratio of our acid to base changing? No, it's not. So that's no fun. Let's change this problem up a little bit. Let's make this 15 milliliters. Okay. That way, the dilution will actually change that ratio. Okay? So we have to account for the dilution. What formula do we use for dilutions? M1V1 equals M2V2. So we're going to have to do that formula twice, once for the acid and once for the base. So if we do the acid, what is the initial concentration of my acid? 0.3. And what volume of that do I start with? 20 milliliters. And what's my total volume now? 35, because I changed that second volume. So from this, we can figure out what the new concentration of acetic acid is. What do you get? What do you get? 0.171. And then we're going to do the same thing with the base. What's my starting concentration for my base? 0.350. What's my starting volume? 20. And my total volume is still 35. Oh, yep, it's 15. You guys lied to me. Forgot that I changed the problem. 15 of my starting volume. All right, so go ahead and calculate that new concentration. You okay there? Tired? What do you get? All right, so now we know the new concentrations. So what else do we need in order to completely solve this problem? We need pKa. Typically, you'd be given the Ka. So we need the Ka of acetic acid. Does anyone know what that is off the top of their head? Because we've used it quite a bit. It's okay if you don't have to memorize any Ka values. It just happens to be one we commonly use, so people just automatically end up memorizing it. Okay. And I think I've pointed this out before, but the Ka of acetic acid is the same as the Kb of ammonia. It's just a weird coincidence. Okay? Yep. All right, so now we're ready to plug this into our formula. So pH equals pKa plus log of, we're going to have the acetate ion over acetic acid. So pH equals, what's our pKa? What is it? Yep, 4.74. So 4.74 here, plus log of, what value are we going to put on the top? 0.150 over 0.171. So go ahead and calculate that pH. It should be close to the pKa, right? Four point what? 683. So we're going to do 3 sig figs. You're always going to base your sig figs off of your concentrations and volumes, never off your Ka, because the Ka is a constant. So use the values given in the problem, like the measured values. Okay. Now, say we did this problem how it was originally written, and we didn't actually change the ratio, that the concentrations both were cut in half, you would have gotten a pH of 4.807. So it's a little bit off. By diluting it and by changing that ratio a little bit, it pulled the pH further from pKa. And it changed that overall ratio of the acid to the base. Okay. The closer that ratio is to 1, the closer the pH will be to pKa. Cool? How do we feel about that? Pretty good? Pretty good? Okay. So I asked you to get out your, oh, nope, sorry, I'm ahead of myself. Now we're going to talk about how buffers will resist those changes in pH. Like you guys were telling me at the beginning of the lesson, what buffers do. We're going to talk about how that occurs. So looking at number 23, we have a solution of ammonium chloride. What is the formula for ammonium chloride? NH4Cl. And we want to know, first of all, what additional reagent is needed to prepare a buffer with ammonium chloride? What part of ammonium chloride do you think we care about? The NH4 plus. We care about NH4 plus. So, because the Cl minus, remember, it's a halogen. Halogens are spectators. They come from strong acids. We don't care about them. Okay. So if NH4 plus is in this buffer, what else must be in the buffer in order for it to be a buffer? NH3. We need the conjugate base of NH4 plus. Okay. And there's my acid-base conjugate pair. All right. Now, like I said, buffers will resist changes in pH because you have both an acid and a base in solution. So depending on what's being added to it, either thing can react to neutralize. All right? So if I add moderate amounts of strong acid to this buffer, give me an example of a strong acid. HCl. What part of that HCl do you think is important? The H plus. You can actually, whenever you see strong acid, you can just write H plus. Because remember, strong acids completely dissociate. So the only thing we're going to care about is the hydrogen ion. Okay. So the H plus is invading this buffer. Which of the substances do you think is designed to react with acid? The NH3, because we want to neutralize it. So the NH3 is going to step forward and react with the invading H+. Okay? Whenever you have a strong substance reacting, that is always a reaction that goes to completion, so it's always going to drive to the right. So we can just put a regular strong arrow. There's no equilibrium with strong substances. It always drives to the right. What is the product of that reaction? H4 plus, the other component of the buffer. Whoa, right? Okay. Now, when you add strong acid to something, regardless of what it is, when you add acid to something, in general, what happens to the pH? It goes down, right? So the pH should decrease. But if this buffer is working properly and there's enough NH3 to neutralize all of the invading H+, that pH will only decrease slightly. And it'll decrease by less than a pH unit. It barely goes down. Okay? And we'll actually do calculations in just a little bit to see, like, oh, depending upon how much, we'll quantify it and give you actual values of, oh, we're adding this much strong acid to this buffer with these concentrations. What's the new pH? And you're going to see that it doesn't change a lot if we're still within the buffering capacity. Okay? Now, for the next scenario, we're adding strong base. What part of a strong base do we care about? OH minus. So we can just say OH minus. So this time, what's invading my buffer is hydroxide. Which part of my buffer is going to react with hydroxide? NH4 plus. That is specifically designed to react with bases. Again, a strong arrow, just like we had with the first scenario. And what are the products of that reaction? NH3, NH2O, the other component of the buffer. NH2O, which is kind of like a spectator, just kind of is there. Okay. So what happens to this pH? It'll increase, but again, hopefully only slightly. Nope. All right. And then for scenario C. So what are your thoughts on this? If we dilute a portion of the buffer with an equal volume of water. So say we have a buffer system and we take 20 milliliters of it and we add another 20 milliliters of water. So the pH should get closer to 7, right? Because we're adding a substance that has a pH of 7, yeah? Why do you say that that's wrong? That's an answer I receive every year. Bring it back to the Henderson-Hasselbalch equation. Equals pKa plus log of, in this case, it's going to be NH3 over NH4 plus. What is happening to this ratio? By diluting it, both of the concentrations, say we cut both the concentrations in half. So what's happening to the ratio? Nothing. It's staying the same. Is pKa changing? No, because it's still the same substance. Ka isn't going to change, therefore pKa is not going to change. So if all the components of the formula are staying the same, why would the pH change? It wouldn't. So pH stays the same because the ratio of NH3 to NH4 plus does not change. The whole thing about adding a substance has a pH of 7 makes it closer to 7, that is completely false. That is a common wrong answer I do receive, though. So I'm really trying to, hammer this home that when you add more water or you change the concentrations, but as long as their ratio is staying the same, pH will not change. Okay? We're going to see this a few other times throughout this unit, so hopefully it'll stick at least once, right? Okay. So, at the beginning of class, I asked you to get out your guided notes, and I asked you to be on what page? 25. On page 25, you have this information on there. Okay, you have this stuff on page 25. So this is the beginning of our Invader problems. Okay. We are going to invade buffers, or really just any solution, with a strong acid or strong base. And after it occurs, one of 4 scenarios will happen. We'll have one of 4 scenarios. So first thing you want to do, though, is deal with the invasion. And that's going to be basically stoichiometry. So we're going to write an equation and use stoichiometry to determine what's left over. So kind of like limiting reaction stuff. I'm going to show you a neat, easy way to do that using what's called a stoich table or a mole table. So we're going to be using moles to figure that out, though. Okay. Then you'll have to deal with what is left over. Okay. If we have any OH minus or H plus left over after the invasion, that means that that substance won out, and you can just do pH equals negative log of H plus, or POH equals negative log of OH minus, and then 14 minus POH. Scenario 1 is nice and easy because there's no rice table involved. There's nothing that's weak. You might have weak things left over, but if you have any of the strong substance left over, it wins out. It overrides the buffer. Okay? It's easy to deal with. We don't want that to happen in our lab. And I'll explain in a little bit with the lab. But we don't want that to happen in our lab. If only the weak acid or weak base is left over, then we're going to do a rice table, putting that in water, doing the hydrolysis, all that stuff. And do a rice table to get to pH. If only the conjugate base or conjugate acid is left over, then we have to do a rice table again. That's salt hydrolysis. That's the stuff we were doing last class. Scenario 3 is everyone's absolute favorite scenario. People don't like scenario 3. Scenario 3, it's the most involved one. However, scenario 3 occurs at the most important part, one of the most important parts of a titration. What part do you think that is? The equivalence point. Scenario 3 occurs at the end point or the equivalence point of a titration. So it's important to know how to do scenario 3. And we'll see all 4 of these scenarios. And scenario 4 is where you have both the weak acid or base and its conjugate. So you still have a buffer left over at that point. So you can just use Henderson-Hasselbalch to find the pH. So scenarios 1 and 4 are nice and easy because they don't require rice tables. 2 and 3 require rice tables, but you need to know how to do all of them. Okay. Let me take a moment to discuss your buffer lab for just a second, and then we'll come back to doing some of these problems. So in your buffer lab, you will be making a buffer that has a pH close to your target pH. And you were assigned which buffer you were supposed to be making, which target pH you had. So you first have to figure out what 2 solutions you're going to have that you need to use. So all of the weak acids will be in solution form already with, I think it's a 0.1 molar solution concentration. And all of the conjugate bases will be in salt form, in solid salt form, but you'll measure out the mass of that. your buffer needs to fall within 0.5 pH units of the target pH. So for example, let's say your target pH is 5. No one's 5. They're all different, but say your target pH is 5. Anywhere from 4.5 to 5.5 and you hit that target pH. You're good. And then I'm going to invade your buffer. I'm going to invade it with either strong acid or strong base. You will not know prior to making your buffer which one I'm invading it with. So you need to make your buffer good enough that it can withstand either invasion. Okay? I'm going to invade it with strong acid or strong base. And after the invasion, I'm going to measure the pH again. And it cannot change by more than 1 pH unit from your initial starting pH. So for example, say that target pH was 5 and you got 4.8. You're good. And then after the invasion, it can't be lower than 3.8 or greater than 5.8. So it's 1 pH unit from your starting pH, not from the target pH. Got it? So your pre-lab, which again, do in 2 classes, your pre-lab is you have to do your calculations to figure out the amounts of your 2 components of your buffer. And there's parameters, the certain volume of the buffer that you're allowed to make and all that stuff. Okay? This is my favorite lab. Okay. So let's do some invasion problems. So with this problem, we have 125 milliliters of 0.525 molar HCl, and that is being mixed with 125 milliliters of a buffer system. That buffer system contains 1 molar acetic and 1 molar sodium acetate. We're going to find the pH of the final solution. So, we have a buffer system. What substances are in that buffer system to begin with? Acetic acid and sodium acetate. What part of that sodium acetate do you think we care about? The acetate ion. We don't care about the sodium. Also, so acetic acid and acetate ion, it's kind of a lot to write out, right? And have you noticed that acetic acid is a pretty common example of what we've seen? So why don't we abbreviate that? Why don't we abbreviate it as HAC and AC minus? So acetic acid is HAC, acetate is AC minus. You can make any abbreviation you want, even on the AP exam, as long as you identify the abbreviation at the beginning of the problem. Like several years ago, there was a problem that had to do with propanoic acid. And again, that was a lot to write out all of those subscripts. A lot of kids just abbreviate it like HPR and then PR minus for the propanoate. So again, as long as you indicate your abbreviation and then you use everything properly throughout it, that's fine. Okay? You don't have to write out the exact formulas of this. You're not drawing the structures or anything for these things. Okay? All right, what are we invading with? What's invading my buffer? HCl. What part of that do we care about? H plus. All right, so my H plus has come invading this buffer system, this buffer castle. Right? My H plus is invading. Which troops are going to be sent out to fight the H plus? The AC minus. And during that battle, the AC minus gets converted into HAC. Okay? I said that this was what type of table? This is going to be a stoichiometry table. This is the stoichiometry. So what did I say we're going to put in our stoich tables? Moles. Like you could go through and do the full out stoichiometry problems. You could totally do that. This table's a little bit easier though. Okay? So we need to figure out the moles of all the substances that we have before the reaction is done. Okay? Before the reaction occurs. So how many moles of H plus did I add? How do I figure that out? We multiply molarity by liters. We know the volume of this acid that we added, 125 milliliters, and we know the concentration, 0.525 molar. So if I take 0.525 and multiply it by the volume in liters, that will get me the moles. So go ahead and do that. What do you get? 0.0656? 0.125 times 0.525 is 0.0656. And how many moles of my acetate ion do I have to begin with? 0.125, because I have 125 milliliters of a 1 molar solution. So 0.125 times 1 is 0.125. What about the HAC? 0.125 as well, because I have 1 molar of that, and we had 125 milliliters of my entire buffer. All right. So this is a stoichiometry problem. So we know that the reaction is proceeding to the right. So we know that the amounts of my reactants are going to decrease and my products are going to increase. And it's going to occur completely. We're going to have none of my limiting reactant left over. Which one is my limiting reactant? H plus. It's the one with the smaller value for the moles. It's the smaller number of troops in this battle, in this invasion. Okay? So all of my H plus are going to be used up. And that same number of AC minus is going to be used up because it's a 1-to-1 ratio. If we subtract from the right, or sorry, if we subtract from the left, we add to the right. So we're going to add 0.0656 because it is, like I said, it's all a 1-to-1 ratio. And if you did full out stoichiometry problems for this, you would get the same answers. Just the table kind of aligns it really nicely for you. Okay? So we're going to have none of the H plus left over. And then for AC minus, go ahead and do that math. What do you get? .0594. And then 0.125 plus 0.0656 is what? All right. What do I have left over? Do I have any H plus or OH minus left over? Nope, so it's not scenario 1. Do I have only my HAC left over? No, so therefore it's not scenario 2. Do I have only my AC minus left over? Nope, so it's not scenario 3. Whew, thank goodness. Don't worry, that's coming. We have both HAC and AC minus left over. We have both components. We have both components of my buffer, so it's still a buffer, so it's scenario 4. It's probably like the second favorite. It's scenario number 4. So we just have to do Henderson-Hasselbalch. So in order to plug this into Henderson-Hasselbalch, we need the pKa. How do we find the pKa? Negative log of Ka, and Ka for acetic acid is 1.8 times 10 to the negative 5. It's okay if you don't have that memorized. It is not a requirement. We've just used it so frequently that it just happens to get memorized. Kind of like the molar mass of water. You end up memorizing it just because of frequent use. All right, and so pKa is what? 4.74. Hey, what was the pH? Because the last problem was acetic acid. It's basically Friday, right? What was the pH before the buffer was invaded? What was the pH before the invasion? What? 4.74 because we had equal concentrations of both component of my buffer. So pH equaled pKa before the invasion. After the invasion, it'll still be close to 4.74 because we still have a buffer. It's just going to be a little bit lower because we added strong acid to it. Okay? So pH equals 4.74 plus log. Ooh, what types of values can I put in this? Concentration. What do I have right now? Ooh, I have moles. So I need to convert that to concentration. So we're going to have to divide both of my moles by what volume? 0.25. But wait, if we're dividing them both by the same volume, doesn't that mean the ratio is still the same? So couldn't I just use moles in the Henderson-Hasselbalch equation? Yeah, I could. Mathematically, I could. However, I caution you against using moles in Henderson-Hasselbalch because scenarios 1, 2, and 3, you have to go back to concentration because it will not work for pH of the strong acid or strong base. It will not work for rice tables if you leave it in moles. For scenarios 1, 2, and 3, you have to go back to molarity. So might as well, since 3 out of the 4 scenarios, 75% of the time, you're going to need to go back to concentration, might as well just be in that habit so you don't make a mistake other places. Okay? If it's only going to save your butts 25% of the time, that's not good enough. Okay? So go back to concentration. So what is the concentration of AC minus? 0.23. Or just 0.238 because we're sig figs. And then 0.1906 divided by 0.25 is 0.762. All right. Now we can solve for pH. Oh. What do you get as your pH? I suggest not rounding till that last step, till it lasts a little bit, just to make sure you don't round off too early and mess up your sig figs later. But yeah, but you're good. If you got 0.238, you're fine. You're fine. Okay, but 4.238. Notice how that's still pretty close to 4.74. If this were your lab, say your target pH was 4.7, you would have gotten 100% on that part of it. You wouldn't lose any points for bad lab technique. Yep. If you look at the rubric, it's your New Year's gift. Okay? All right. So, shh. We have one more problem we're going to do. It might be a scenario 3. It might be. Let's see. Let's see what ends up happening. Let's see what happens. So, have you read the problem yet that I have up on the board that's on your paper as well?
Yeah, mine does that too.
All right, so what is my solution that is being invaded? Acetic acid, so we can abbreviate that HAC. Do I have any acetate ion? No, so this isn't a buffer. This is just a weak acid. And what am I invading that with? Strong base. So what is the formula? OH minus. So I'm invading my weak acid with a strong base. Kind of like what you did with your previous lab. You had just a weak acid and you invaded it with strong base. Okay? All right, so now let's write out that equation. When OH minus reacts with HAC, because those are the only two things there, what are the products? Water and AC minus. Okay? What values or what units of things can I put here? This is stoichiometry, because we have a strong arrow, so moles. So always at the beginning part of the invasion, the reaction of the invasion is always going to be moles. So you're always going to do a mole table, and then you might have to do a rice table as well. Because we're reacting with a strong base. The strong base is going to force it to go to the right. All right. So how many moles of OH minus do I have to begin with? And how many moles of acetic acid? The same thing. How many moles of AC minus do I have to begin with? 0. And what about the water? We don't care about it. There's many moles of water to begin with because sodium hydroxide and acetic acid are both dissolved in water, but the amount of it doesn't matter. Because it's like a spectator. Or if we're going back to our invasion scenario, the H2O is just like a peasant. Or like a horse. I don't know. It doesn't matter. Okay? So, what do you notice about the amounts of both of our reactants? They're the same. So which one's my limiting reactant? Neither or both, however you want to think about it. But we have a complete reaction, right? It's equal molar concentrations or equal molar amounts, right? So both of these are going to get completely used up. And we're going to have 0 of both of those. And we're going to add that same amount to the right. At what point of a titration do you have exactly the same amounts of your acid and your base? At the equivalence point. So this occurs at the equivalence point. What else do you know happens at the the equivalence point? What scenario? The third one. So this is scenario number 3 because we only have the conjugate base left over. We only have the ion left over. We don't have the original weak acid or weak base. Okay? All right. So, in order to, what do I do next? A rice table. And in my rice table, I'm going to have the Bronsted-Lowry reaction of the acetate ion with what substance? Water. Now, this is in equilibrium. This has an equilibrium arrow because there's an equilibrium constant associated with this reaction. What are the products of this reaction? HAC and OH minus. Okay, we don't care about water, just like we've never cared about water. The initial amounts of HAC and OH minus here are 0 because we're going back to equilibrium from the AC minus in water. What value do I put as my initial for AC minus? Wrong. Because 0.0625 is the moles I can only put concentration in a rice table. So I divide this by 0.250 liters, right? Because we had 125 plus 125. And 0.0625 divided by 0.25 is 0.25. So that's what we put here. Whew. Don't worry, we're almost done. What are my changes? Minus x for the left, plus x for both things on the right. All right, so let's go ahead and write the equilibrium expression for this reaction. Is it going to be a Ka or a Kb? Look at the reaction. Kb, because I have OH minus. Okay, so I have that. But wait. If I look up in, well, yeah, of course there's more. We haven't even found the pH. If I look up in the textbook, I'm not going to find a Kb of acetate ion. However, I can find a Ka of acetic acid.
So you can solve for Kb because Ka times Kb equals Kw.
Exactly. Ka times Kb equals Kw. So if I take Kw, which is 1.0 times 10 to the negative 14, and divide it by Ka, I'll get Kb, which is 5.6 times 10 to the negative 10. This is why scenario 3 is awesome, because there's so much like converting things back and forth. I know. So 5.6 times 10 to the negative 10 equals x squared over, oh wait, can I make this minus x negligible? You need to check. You're going to check 0.25 against what? The Kb, the 5.6 times 10 to the negative 10. And what is 0.25 divided by 5.6 times 10 to the negative 10? Really big number, like really larger than 400. So we can get rid of that. Because x is going to be so much smaller than the initial concentration that the amount we're going to be subtracting is negligible. So x squared over 0.25. So when I solve for x, what concentration is that will help me get to pH? OH minus. That's going to help me get to pH through a couple calculations. And what do you get as your x? 1.18 times 10 to the negative 5. And then through a couple calculations, you should get the pH equaling what? If I do negative log of that, right here I get POH, and then 14 minus that. 9.07. 9.073. 3 sig figs. Yeah, totally right here. These were both 0.500s. So we had 3 sig figs in all my values of the problem. So we maintained 3 sig figs throughout.